Hi everyone, my name is Abdelraouf Ouadjaout, and I will present to you a work that I have done with Antoine Miné on a language for modeling library functions that we use in order to analyze real-world C programs by abstract interpretation. So the approach is to model library functions instead of using their actual implementation because the source code of the implementation can be unavailable, and also because the implementation can be too complex and we just want to model a simplified version of the function. So we use a logic language in order to express the specifications of the function because logic formulas can be more expressive than C, and also we want to avoid hard coding the semantics of the library functions inside the analyzer, so we let users refine the models if they want. And we formalize the semantics of the language using abstract interpretation. So we define the concrete semantics of the language and we develop some abstractions. And here is a running example that is a very simple version of the WC command line utility that counts the number of bytes in a file. So it starts by opening the file using the function fopen, and then it reads the file using the function fgets, and fgets retrieves a chunk and stops either when encountering a new line or when reaching the maximal capacity of the input buffer. And after that, we can get the number of retrieved bytes using the function strlen. And now let's see how we can model some of these functions used in this example. And let's start by the function fopen. So we start by expressing the preconditions of the function. And in this case, the precondition is that the parameters path and flags should point to valid strings, which means that the pointed memory blocks should contain somewhere a null terminating byte. And after that, we want to specify that the function fopen will create a new file descriptor. However, we don't want to specify how the file descriptor is created, how it is stored, etc. So we use the general concept of resources, which are system objects created by the stub, but they have an arbitrary content and size. So the only information that we have is the class of the resource, which is here the file class. And using this simple concept, we can easily model other things like dynamic allocations with malloc, creation of sockets, and so on. And let's see how an allocation actually works. So an allocation is a side effect. And in our semantics, we represent an execution of a stub as a relation between an input and an output environment. So side effects are applied only on output environments. And in addition, we attach to the allocated resource some metadata, such as its class, its size, and a liveness flag. And it is important here to note that allocations are non-deterministic side effects, which means that the size and the content of the allocated blocks are arbitrary. However, we can refine the post state using the statement ensures in order to keep only some cases. For example, here we want to ensure that the allocated block has the size of one file descriptor. However, we keep the fact that the content of the file descriptor is still arbitrary. Now let's move on to the specification of the function fgets. So when calling the function fgets, we should verify that the parameter buff is a valid pointer and that it points to a memory block that has enough space in order to receive at most n bytes from the file. And finally, we have to check that the file descriptor is still open, which means that the pointed resource is a member of the file class and that the resource is still alive. Now we want to model the fact that we put some data inside the input buffer, which is done using the statement assigns. that expresses the fact that some part of the output state has been modified with some random value. And here is how assignment work. So similarly to allocation, assignments are also non-deterministic side effects applied only on the output environment. Similarly also to allocation, we can refine the post state using the statement ensures, but the thing here is that we have to use the primed notation in order to refine the value of a modified buffer in the output state. For example, we know that the function fgets always puts a null terminating byte in the reception buffer, so we can express it by ensuring that one of the modified bytes should be null. So that was a very quick overview of the Stub language, and you can find more details about the concrete semantics of the language in the paper. And to implement an abstraction of these semantics, we have used Mopsa. Mopsa is an open source framework for developing static analyzers by abstract interpretation. It features a modular architecture that supports multi-language analysis, and in contrast to other analyzers, Mopsa doesn't translate statically the input programs into a fixed intermediate language such as LLVM, but instead it has an extensible IST that domains can extend in order to add new languages. And for our case, for example, we have extended this IST in order to include both C and the Stub language, so we can mix at the same time logic formulas containing C expressions. So after building the IST, Mopsa searches for a configuration file written in JSON that describes which domains are used and how they are combined. And after constructing the global abstraction, the analysis can start. So during the analysis, domains can interact only via some concrete semantics, for example, executing a statement or evaluating an expression of some language, or they can ask some generic abstract queries, for example, to retrieve the interval of a numeric expression. So there is no direct dependency between abstractions because domains rely on concrete semantics of other domains. So this ensures a low coupling between domains, so we can add or change abstractions very easily. Now let's take a look on how the semantics of the Stub language is abstracted. So assume that we have a working abstraction of C, no matter how it is abstracted, and assume that we have also some universal abstractions like a numeric domain. And now on top of that, we have added 4 generic domains. 2 of them are independent of any language. So they are used here with C, but we can also use them with, for example, Python. So we have the iterator domain that handles the intraprocedural flow inside the stub by executing the statements of the stub in the appropriate order. And we have the second domain, which is a generic evaluator of quantified formulas. So it basically translates them as while loops so that we can use unrolling, widening, or other iteration policies. We have also 2 other domains that depend on the semantics of C, but they can be used with any abstraction of C. So the first domain is an abstraction of relations that represent a pair of C environments as a single environment by appropriate renaming of variables. And the second domain is for managing resources so that they appear like C blocks from the heap. And here is an example configuration. So for C, we have 2 main domains. We have the string length domain, which is an abstraction of C strings that remembers the position of the first null byte and keeps it in a numeric variable called slength. And we have also the classic pointer-based offset domain that keeps the bases and the offsets of a pointer in separate variables. And for the universal part, we have polyhedra for numeric part, and we have also the recency abstraction for abstracting heap addresses. And here is an example of an abstraction. So for the pointer buff, so its base is the chunk array, and its offset is 0. So this is as precise as the concrete state. And for the chunk array, we have only the information that the length of the string inside this array is 0, because the first byte is null. We have no other information about the other bytes. And now let's see how we can lift this abstraction to represent relations. So the idea is very simple. We represent a pair of states as a single state by just renaming the modified memory blocks. For example, here, the modified block is the chunk array. So we have, in addition to the input version, we have also the output version denoted as primed chunk. So since it is viewed as a normal C variable, we can apply on it existing abstractions directly. For example, here we can apply the string length abstraction on primed chunk. And naturally, when we apply a filter on primed expressions, this is automatically reflected on the primed version. So we see that the length of the primed chunk decreased because we ensured that there is actually a null byte somewhere in this buffer, in the output state. So we use it here, quantified formula to do that. And now let's see how we can handle them in our analysis. So let's illustrate that through an example of calling the function strlen on the chunk array. So the stub contains some quantified formulas, and as I have said earlier, we have a generic domain to handle them as loops. While this works without modifying the existing C domains, which is fine, we can be more efficient or more precise if we let the C domains handle quantifications more symbolically and more locally. And now let's see how it works. So when we reach the predicate at line 4, the domain string length can use this rule to evaluate the formula symbolically. So the rule says that to have a null byte in the range min max, it is necessary that max should be after the S-length offset, because all bytes before are different to 0. So if we apply this on our state, nothing changes because the predicate is always true. Now, since this predicate is a requirement, we should check its negation to see if there is an alarm. And the domain string length has this rule to evaluate such for all quantification, which says that in order to verify that all bytes are different than 0 in range min-max, it is necessary that the terminating null byte should be outside this range. And if we apply this rule, in this case, we obtain bottom, which is good because this proves that the string in the chunk array is valid. Now let's move on to the next statement, which is a simple buffer. So it just refines the value of the return variable. So it's bounded now by 255. And now to evaluate this predicate, the string length domain has also a symbolic rule that says that that a byte is equal to 0 if the offset is greater than the S-length variable. So here, if we apply it, we see that the return value of strlen is now greater than the S-length variable. And now we can refine the return value using the last statement. So we can use here the rule number 2 as previously, and if we apply it, we can find that now the return value of strlen is equal to the slength variable, which is the invariant that we are searching for. Now for testing our abstraction, we have first created models of more than 1,000 functions from the GNU standard library, and we have run some tests from the Juliet benchmarks. So each of these tests targets some bug identified by CWE, like buffer overflows, integer overflows, etc. And each test contains two cases or two functions. So there is one good case that doesn't contain the bug, and there is a bad case containing the bug. So we run Mopsa on all these tests, and we report here the analysis time and the precision. So the green flag is for a precise analysis, where the good function is reported as safe, and for the bad function, Mopsa finds exactly one alarm. And the orange flag is for an imprecise analysis. So as you can see here, in many cases we are precise. However, we have some issues with mainly integer overflows tests because the domains are not very precise, so they need to be refined in order to improve the analysis precision. And we have also analyzed some programs from the Coreutils package, which is a collection of well-known command line utilities, such as Who Am I, ls, and so on. We have analyzed only 90 programs, and for each program we have tested 3 scenarios. So the first scenario is when calling the program without any command line argument. And the second scenario is when we call the program with one symbolic argument, which means that the argument is a valid string, but containing arbitrary content and having an arbitrary size. And the third scenario is when we call the program with an arbitrary number of parameters, and each parameter is a symbolic string. So here we see the analysis time and the number of reported alarms. So in general, the analysis takes a few minutes. However, as for the Juliet benchmarks, the analysis can be imprecise. So we have to work more in order to improve the precision of the analysis. So in conclusion, this talk was about a language for modeling and specifying library functions. It is developed within the Mopsa framework, and we have presented some preliminary results on the analysis of Juliet and some programs from Coreutils. And as future work, we plan to add support to more libraries, for example, OpenSSL, and also it will be nice to see how we can use the same language to model library functions in Python. And finally, we want to address the precision issues also. And as a final word, there is a pre-release of Mopsa available online, so we will be very happy to have your feedback. And thanks for listening.